Hello and welcome to a new video on IGCSE Physics Classified Paper 4. In this video, we shall discuss the Sun and the solar system. The Sun mostly consists of two elements. State the two elements. Of course, the two elements that are present mostly in the Sun, or that are mostly present in the Sun, are hydrogen and helium. And we will discuss this in more detail. Most of the radiation from the Sun consists of visible light and two other regions of the electromagnetic spectrum. State the name of one of the other two regions. Of course, you only need to mention one, but I mentioned both just so that you would know them. Ultraviolet and infrared. So the Sun transfers light and heat to the Earth. This is in very simple terms. So light is visible light, basically, and heat is infrared radiation. But you're also advised to put sunscreen and sunblock when you're at the beach, for example. And this is to protect your skin from the harmful effects of ultraviolet rays. So from real life applications, you should know that visible light, infrared, and ultraviolet are the three most frequently observed radiations coming from the Sun. The highest energy coming from the Sun comes in these three spectrums. Complete the sentences about the Sun. The Sun consists mostly of the elements hydrogen and helium. Most of the Sun's energy is radiated in the infrared, visible light, and ultraviolet regions of the electromagnetic spectrum. So we've already discussed this before. Again, I'm just showing you how different questions are actually asking about the same thing and how popular this topic is. It's coming up very frequently in past papers. So the Sun is our nearest star. State the three main forms of electromagnetic radiation emitted by the Sun. Again, infrared, visible light, and ultraviolet. And state the two main elements that are found in the Sun. Again, these would be hydrogen and helium. Now we will discuss in further detail how hydrogen and helium interact together. So the Milky Way is one of many billions of galaxies. Each galaxy contains many billions of stable stars. Stable stars, like the Sun, transfer energy into space by emitting electromagnetic radiation from their surfaces. Describe what happens in the core of a stable star to release energy that is eventually transferred into space. So we're discussing two things here in this video: how the energy is formed and in which spectra is it released. So in which spectra? We said infrared and visible light and ultraviolet. How is the energy itself formed? This occurs by nuclear fusion, and nuclear fusion happens when two hydrogen nuclei fuse together or combine together to become a helium nucleus. So this is how energy is formed inside the Sun, nuclear energy, of course. The process of energy release in the core of a star is different to the process of energy release in a nuclear reactor in a power station. Describe how these processes of energy release are different. So in stars, we said nuclear fusion occurs where light nuclei like hydrogen join together to form a heavier nucleus. So in a sense, for fusion, we have two light nuclei, two small nuclei combining together to form a larger nucleus. In case of the Sun, we have hydrogen nuclei, and when they combine together, they form a helium nucleus. What happens in nuclear reactors, though? So these are the two types of nuclear processes: nuclear fusion, and the second process, that we're going to talk about is nuclear fission. So what is nuclear fission? It is the opposite of fusion. So you have a heavy nucleus, like for example uranium, and it splits into two lighter nuclei. So this happens inside reactors, and this is how nuclear reactors create or convert, in a sense, energy into nuclear energy. So nuclear fission happens inside reactors and nuclear fusion happens inside the Sun. This is how they are different. Next, we move on to the solar system. And we start with basic concepts. Gravitational field strength is measured in, so this actually has to do with mechanics a little bit. You were told before that F equals ma, force equals mass times acceleration, and a special type of force is the weight. The weight is equal to mass multiplied by g, where g is the acceleration due to gravity. The acceleration due to gravity has another name, which is gravitational field strength. So this is actually g, and g is equal to weight divided by mass. So the weight is a force, so it has a unit of newtons, and mass is measured in kilograms. Therefore, the correct answer here would be Newton per kilogram. This question is about the solar system. The object at the center of our solar system is, of course, the sun. So in our solar system, the central object is not a comet, it's not the Earth, it's not the moon, it's the sun, and the planets revolve around the sun. List the 4 planets closest to the sun in order of their distance from the sun. One is done for you. So you need to know the order of the planets. Of course, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and we used to have Pluto, but now it's not really a planet. Now we call it a dwarf planet. So there used to be 9, now there are 8. Mercury, Venus, Earth, and Mars are the 4 that are close to the sun. And then we have Jupiter, Saturn, Uranus, and Neptune. These are the ones that are far away from the sun. Figure 11.1 shows the sun and the 4 innermost planets, A, B, C, and D of the solar system. In table 11, write the names of the innermost planets. One is done for you. So, of course, again, they're Mercury, Venus, Earth, and Mars. And I want you to notice that Mercury is very small compared to Venus and Earth. So this is Mercury, this is Venus, this is Earth, and this is Mars. Venus and Earth are somewhat similar sized. Maybe Earth is a little bit larger, but Mercury is much, much smaller than the rest. And it's also the closest planet to the sun. Figure 11.1 represents the sun and part of the solar system. Complete the labels on figure 11.1 by writing on the dotted lines. So, of course, the innermost orbit belongs to Mercury. So the innermost planet is Mercury. And then for the second level, we have Venus, like we said. And then for the third level, we have Earth. So Earth is the ball inside. So this is Earth here. And then around the Earth, we have a moon that is rotating around the Earth, which is why we see the moon, of course, at night. These are all very simple questions. Figure 10.1 represents part of the solar system. State the name of planet A and the name of planet B. Of course, like we said before, planet A is the closest to the sun. This is Mercury. Planet B is the 4th planet here, so it has to be Mars. So this is why we have Mercury here and Mars in the answers. On figure 10.1, draw an X to represent a moon of Jupiter. Draw a line to show how this moon moves. So we have Jupiter, and of course, all that we have to do is just draw the moon. Of course, this orbit is very large, so a more accurate answer here would be like something like this. Or even smaller than that. It rotates very close to the planet. So like the best circle to draw here would be like something that is very, very close to Jupiter. It rotates around Jupiter. It doesn't have such a wide rotation. It just has a very small rotation around Jupiter. But they won't really take this too much into attention. Whether you draw it small or large, I don't think this will matter. However, just for accuracy, bear in mind that the moon closely revolves around Jupiter. State 2 ways in which the 4 planets nearest to the sun are different from the 4 planets furthest away from the sun. So like we said, this is the sun here. We have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. So they're kind of divided. On the left, we have the 4 that are closest to the sun, and they are relatively small, and they are formed mostly of rocks, so they're rocky. and the other four are relatively large, and they are formed mostly of gas, so we call them gaseous planets. So this is the distinction between both groups. So like we said, number one would be that the four nearest planets are rocky, the four furthest planets are gaseous. Number two would say that the four nearest planets are small or relatively small, and while the four furthest planets are relatively large. Figure 11.1 represents the Earth in orbit around the Sun. State the name of the force that keeps the Earth in orbit around the Sun. Of course, the reason why the Earth is revolving around the Sun is because of gravitational attraction. So the Sun, a much larger body than the Earth, by the way, so this drawing isn't very accurate. So if this is the Sun, then this would be the Earth. or even this is not accurate. The Sun is much, much larger than the Earth. But anyway, so the Sun, as a very large object, attracts the Earth towards it. And this is why the Earth is rotating in a circular orbit around the Sun, or an elliptical orbit around the Sun. So gravitational attraction would be the correct answer here. State the time taken by the Earth to complete one orbit of the Sun and include the unit. Of course, 365, or more accurately, 365.25 days, which would be the number of days in 1 year, of course. State the time taken by the Earth to rotate once on its axis and include the unit. So the time for one rotation is the time of 1 day, which is basically 24 hours. Finally, the Sun consists mainly of two gases. State the names of the two gases. We said this before, they are hydrogen and helium. These are all very simple questions. We will move to more advanced ones very soon. Table 9.1 gives information about 3 planets in the solar system. State the name of planet X. So maybe you'll remember at the beginning when I told you, keep in mind that Mercury is very small and Venus and Earth are somewhat equivalent in size. Earth might be slightly larger. So what would planet X be? Because planet X has two properties. First of all, it is closer to Earth than the Sun. So it has to be either Mercury or Venus. We don't have any other option because we have Mercury, Venus, Earth, and this is the Sun here. So anything that is closer to Earth, closer to the Sun than Earth, has a smaller distance than Earth, must be either Mercury or Venus. But is it Mercury or is it Venus? First of all, they're very close in terms of distance and they're very close in terms of mass. So this would not be Mercury. This would have to be Venus. Mercury is much, much smaller than the rest. Describe the relationship shown in table 9 between the mass of a planet and the gravitational field strength at the surface. Maybe you know this in advance, maybe you don't, but either way, you can just observe that we have 3 masses here. Jupiter is much larger, of course, than the rest, and it has a much stronger gravitational field strength. And Earth is the second largest, and it has the second strongest value for gravitational field strength. So we can just observe that the greater the mass, the greater the gravitational field strength. Explain why distance from the Sun is an average value. This is because the orbit of the planets is not exactly circular. It's maybe approximately circular at some points, but it's mostly elliptical. And because it's elliptical, the radius is not the same. So for example, if this is the Sun here, one planet may revolve on this path. So of course here it's very close to the Sun, whereas here it's farther away. So therefore, we can't really say that we have a fixed radius of orbit. We have a changing radius, and this is why we need an average value. So the average distance from the Sun varies at different phases of the orbit. Hence, the radius changes. And we're going to discuss in this video how this affects the energy of the orbiting planet, but it comes in the more advanced concepts. And there we are, advanced concepts. The Chandra telescope also orbits the Earth, but does not move in a circular orbit. Its distance from the Earth and its speed change as it orbits the Earth. It travels fastest when it's closest to Earth. Using ideas about energy, explain why this is the case. So we have planet Earth. We have a moon or a telescope or a satellite or whatever orbiting in an elliptical path, maybe around the Earth. So what they're saying is that it's fastest when it's closest to Earth. So let's compare these 2 points. Here it's going to be fastest. And here maybe it's going to be slowest. And we want to discuss in terms of energy. Of course, fast and slow describe speed, and speed is related to kinetic energy. So you can deduce that here we have a very high kinetic energy, and here we have very low potential energy. However, the total energy of any body that is rotating or moving or whatever, the total energy is conserved. So the fact that it has high kinetic energy at some point, excuse me, I'm very sorry, this is low kinetic energy, not low potential energy. I'm very sorry. So the fact that it has high kinetic energy at a point and low kinetic energy at another point must indicate that there is another form of energy in interplay in this case. So what would that energy be? Of course, this would be gravitational potential energy. And when the kinetic energy is high, it makes sense that the potential energy is low. And similarly, when the kinetic energy is low, it makes sense that the potential energy must be high. So that the sum of kinetic and potential energy, so Ke plus Pe, must be constant all the time. And can we explain why the potential energy is low when it's close to the Earth and the potential energy is high? You studied this before on Earth when we said that if we have like the ground and we have a moving body, as the body falls to the ground, what happens? The potential energy decreases and the kinetic energy increases. So it's a similar concept. As the body gets further away from the attracting body, of course, the ground here represents the attraction of the Earth. So the Earth is attracting a ball towards it. So as the ball gets closer to the Earth, its potential energy decreases and its kinetic energy increases. However, if the ball is much higher up, it has a higher potential energy because potential energy is related to height. So just like on Earth, potential energy is related to height, in space, potential energy is related to distance. So if the planet or the moon or whatever if the moon in this case or the satellite is close to the Earth, it has low potential energy and high kinetic energy, just exactly like this case here, when it's close to the floor. And when it's far away from the Earth, it has high potential energy but low kinetic energy. And this is similar to the case where it is at a great height above the floor. So it's the same concept, just in a different setting, except instead of discussing an object on Earth, we're discussing an object in space. So the answer is pretty simple. Because the total energy is conserved and it is the same everywhere, when closest to Earth, the potential energy is minimum and kinetic energy is maximum. Therefore, the speed is maximum. Pluto is a dwarf planet. Figure 10.1 shows the direction of motion of Pluto as it follows its elliptical orbit around the Sun. Point X is the point in the orbit closest to the Sun, and point Y is the point furthest away. The orbital speed of Pluto varies as it orbits the Sun. Describe how the speed of Pluto varies as it moves from X to Y and then back to X. So they didn't really tell you when it is fastest and when it is slowest like they did in the previous question, which was easier. Here you have to figure out for yourself when would it be fast and when would it be slow. Like we said before, you can always remember the model of a ball and the ground. This is the ground here. So we have the ball at two different places. Here it has low potential energy, high kinetic energy. And if it's at a greater height, it has high potential energy and low kinetic energy. So same thing applies in space. When it is at X, this is similar to being close to the floor. So it has low potential energy and high kinetic energy. When it is at a farther distance away, like Y, it has high potential energy and low kinetic energy. So moving from X to Y, what happens? Potential energy increases, kinetic energy decreases. So describe how the speed of Pluto varies as it moves from X to Y. So from X to Y, since the kinetic energy decreases, we can say that the speed decreases from X to Y. And of course, if we're going back from Y to X, from Y to X would be this path here. we are getting closer to the sun. And since we're getting closer to the sun, we will do the opposite. We'll say that the speed increases because the kinetic energy increases, similar to the ball that is getting closer to the ground. Explain in terms of energy transfers why the speed of Pluto varies in this way. So in terms of energy transfer, we discussed this before. We said that the total energy is the same everywhere. And as Pluto gets farther away, the potential energy increases and the kinetic energy decreases. So at X, the potential energy would be minimum. Like we said, at X, the potential energy is minimum and the kinetic is maximum. And at Y, the opposite occurs. Describe how the four innermost planets of the solar system were formed. So this is something you also need to know and you need to understand. So it began by clouds, we call them interstellar clouds of dust and gas orbiting the sun, and they consist of many different elements or particles. The rotation around the sun leads to combining of particles or accretion. It's called the accretion model because particles combine together. And this led to the formation of large rocks and boulders. Boulders are very large rocks. And then due to gravitational attraction, these boulders got attracted together and accretion disks are formed. And then due to continued collisions, a planetary core was formed. So basically, small bodies got attracted together, forming larger bodies which got attracted together. And then these formed what we call the planetary core. And you need to understand how this happened. So figure 9 shows the sun as the central dot and the planets Saturn, Jupiter, and Earth labeled S0, J0, and E0. The planets orbit the sun anti-clockwise. From the Earth's orbit, the planets appear aligned. So initially, E0, J0, and S0 all fall on the same line, as you can see here. Of course, the blue balls are not part of the diagram. They're part of the answer, which we're going to discuss right now. So initially, these were not there. Assume that Saturn takes 30 years to orbit the sun and that Jupiter takes 12 years to orbit the sun. On figure 9.1, mark the positions of Saturn and Jupiter 5 years after the original positions shown. Label these positions S1 and J1 and show your work. So we need to think of this in terms of angles. Of course, you need to know that the angle around a circle, a complete circle, is 360 degrees. So one complete rotation involves 360 degrees. So if Saturn takes 30 years to orbit the sun and Jupiter takes 12 years to orbit the sun, and we know that Earth takes 1 year to orbit the sun, of course. So on figure 9.1, mark the position of Saturn and Jupiter 5 years after the original position. So how long or like how much of the path would they cover in 5 years? So for Saturn takes 30 years, and we want to know where it will be in 5 years. So 5 over 30 describes the fraction of the cycle that it has already executed. So out of 30 years, we've completed 5 years. So we've completed 5 over 30 of the cycle. And the cycle, we said, is 360. So it should be at a 60-degree angle from where it initially was. So we're assuming that this angle here is roughly 60 degrees, and they don't want you to measure it with a protractor or anything. As long as you state that the angle here is required to be 60 degrees. Same thing for Jupiter. It takes 12 years to complete one cycle. So we want to know how much of the cycle it has completed, and that would be 5 divided by 12. And we multiply by 360 to get the angle. So the angle is 150. So we just assume that this angle here is like 30, for example, so that the large angle here is roughly 150 degrees. Again, these are general or basic or abstract locations. You don't really need to measure them exactly. But for example, you want 150 degrees, so you cannot put J1, for example, anywhere here. This would be completely wrong because this would be a 90-degree angle or less. So this here is a 90-degree angle. You want 150, and this here in total would be 180. So if this is 90 and this is 180, you want to be somewhere in the middle, somewhere here, probably closer to the 180. So this is a correct position for J1. BI says on figure 9.1, mark the position of Saturn and Jupiter 20 years after the original positions shown. So instead of 5 years, we're going to do the same calculation again for 20 years. Pretty much the same idea. For Saturn, it's 20 over 30 instead of 5 over 30. So we get a 240-degree angle. Like we said, if this is here, so let's just divide into 4 quadrants like this. This is 90, this is 180, this is 270. So we're looking at 240, which would be somewhere around here. So this makes sense. Of course, maybe let me just draw this nicely. Let me draw this again, excuse me, just so we're not confused. Like we said, we're dividing into 4 quadrants. So this would be 90, this would be 180, this would be 270, and this is a good estimate here for 240. So Saturn seems correct. Let's move on to Jupiter. Jupiter takes 12 years, and it has been rotating for 20 years. So 20 over 12, and we get a number that is actually larger than 1, and that's okay. We multiply by 360, we get 600 degrees. So how would we graph 600 degrees? One complete rotation is 360. So 600 is basically equal to 360, which is one complete rotation. That would return back to J0, its initial position. So this here would be 360. And it would return back to its original position, and then it would start another cycle. So 360 plus something equals 600. So all we have to do is just subtract 600 minus 360. We get 240. So of course, since both of them are 240, they must be aligned. So we had to draw the 2 circles here on the same line from the perspective of the Earth. State what is observed from the Earth's orbit after 20 years. That's what we were just explaining, that Jupiter and Saturn must be perfectly aligned. The average temperature on the surface of Pluto is 43 Kelvin. Convert this temperature to a value in degrees Celsius. You should know that Kelvin minus 273 is equal to degrees. You should remember this by, of course, you should remember the number 273. And you should remember that there is 0 Kelvin is the minimum temperature. So Kelvin can only be 0, it cannot be negative. But degree can be negative. So 0 becomes negative 273. And this reminds you that to go from Kelvin to degree, you just subtract 273. This is what we do here. We do 43 minus 273, and that gives us negative 230 degrees Celsius. Pluto has a white surface. As shown, as Pluto rotates, the white surface alternately faces towards and away from the sun. Explain how this affects the temperature of Pluto as it rotates on its own axis. So of course, we have a white surface and a dark surface, and we should know that white surfaces are good reflectors, whereas black surfaces are good emitters and absorbers. So therefore, since white is a better reflector, you should know this from thermal physics, white surfaces will experience a lesser increase in temperature than black surfaces when facing the sun. Finally, we move on to calculation-based questions. Figure 11 represents the Earth in orbit around the sun. The speed of visible light is 3 times 10 to the power of 8, of course. Calculate the time taken for visible light to travel from the sun to the Earth when the Earth is in the position shown, excuse me. Of course, this is very simple. This is just a very basic equation of distance equals speed times time. And you are required to find the time, so you should be comfortable with the mathematics of this. So D equals VT. Here we want the T, so we want to isolate the T in a sense. So T would be D over V. And the distance and the velocity are both given. There they are. This is the distance. This is the velocity. All we have to do is just divide them by each other. So 1.5 times 10 power 11 over 3 times 10 to the power of 8 gives us 500 seconds. It's a simple matter of dividing the distance by the time. This has the unit of meters, so we know that this is the distance. And this has a unit of meters per second. We know that this is the speed. And all you have to figure out is that time equals distance over speed, and you do the calculation. I would recommend that you do not write the entire thing on the calculator at once, because this tends to bring out wrong answers. I would recommend that you would just figure this out on the calculator alone. So 1.5 divided by 3, this would give you 0.5. And then 10 power 11 divided 10 power 8, this would give you 10 power 3, because you just subtract the powers. So 11 minus 8 gives you 3. And this is actually your final answer, and it becomes 500. The distance between the sun and the earth is 1.5 times 10 to the power of 11. The speed of an electromagnetic wave is 3 times 10 power 8. Calculate the time taken for an electromagnetic wave to travel from the sun to the earth. Again, this is the exact same question with the exact same numbers, though in a different exam. Again, this is the distance, this is the speed, and we use the exact same formula to get the exact same result, 500 seconds. Visible light from Mars reaches the Earth. The speed of light is 300,000 kilometers per second. Show that when the planets are 170 million kilometers apart, it takes about 600 seconds for light to travel this distance. We want to show that it takes 600 seconds for light to travel. So again, we just say d equals vt. So t equals d over v. And we replace d and v with the corresponding values. Of course, since the speed here is given in kilometers and the distance is given in kilometers as well, all you have to do is just replace with the numbers without doing any conversions. So you have 300,000 divided by 170 million. Excuse me, it's the other way around. I apologize. The distance is 170 million. I apologize for this. 170 million here over 300,000. So you cross out 5 zeros, and you're left with 1,700 over 3. And this gives you 566 seconds, which is approximately equal to 600 seconds. This brings us to the end of our video. I hope this has been beneficial. Thank you for watching.